Hi, I'm Paloma Suri, and today I'll be presenting our work PatchGraph Enhanced Tactile Tracking with Learned Surface Normals. Our goal is to estimate latent object poses X, given a sequence of tactile image measurements Z from a vision-based tactile sensor. We formulate this as an inference problem over a factor graph that optimizes for the most likely states X given measurement C. We leverage the fact that tactile images fundamentally capture surface normal information about an object. The image on the left from Yuan et al. Illustrates this physics of tactile image generation. So when an object presses on an elastomer gel and deforms it, the color and intensity of illumination at each pixel correlates with its local surface normal. Our key insight is to exploit the observation that novel objects can be thought of as being composed of known surface patches. So we can go from a tactile image to predicting surface normals that we then integrate to create a local surface patch map. This enables us to track objects over time without relying on prior object models in both sim and real. So we propose a two-stage approach. In the first stage, we learn a mapping from tactile images to surface normals using an image translation network. In the second stage, we use these surface normals within a factor graph to both reconstruct a local patch map and use that to infer 3D object poses. So in stage one, we extract ground truth surface normals for both sim and real data. We then use a pix-to-pix image translation network, which trains a conditional GAN, in which the generator predicts surface normals from tactile image inputs, and the discriminator classifies ground truth as real and predicted as fake images. In stage two, we construct a factor graph where variables are the latent object and sensor poses, and factors are constraints between these variables. So image-to-image factors in blue encode relative poses between consecutive frames. Image-to-patch factors in red encode relative poses between a keyframe and a fused local patch map. We also include global pose priors as unary factors on the end effectors and the first object pose. So for simulation trials, we collect data using the tactile simulator, where one can load the digit sensor, an object, and render high-resolution tactile images. We collect data for a diverse set of objects, a sphere, a cube, a toy human, and a toy brick. For real-world trials, we mount the object on a workbench and the sensor on a movable plate tracked by a motion capture system. Here we move the sensor with respect to the object and collect data for two shapes, a sphere and a pyramid. So let's look at results for the surface normal predictions. We test the model on unseen shapes such as real pyramid and toy brick and see that our predictions using our pix-to-pix model is able to generalize across shapes with predictions close to ground truth. On the other hand, a per pixel MLP model baseline finds it difficult to generalize from sim to real data due to changes in sensor characteristics such as lighting. Now let's look at the final tracker performance on the SimCube object. We see that compared to baselines such as constant velocity and only image-to-image factors, PatchGraph has the lowest tracking errors, closely matching ground truth patch performance. We see a similar performance trend on a different object, the sim toy human. Note that we only use the local patch map in light green for tracking and do not use the object model. For real trials, we look at these qualitative reconstructions fused based on estimated poses, and unlike baseline, PatchGraph is able to recover a consistent 3D object geometry. We see this trend quantitatively as well, where we are able to achieve low final rotational and translation tracking errors. For more details, please check out our paper, and thank you for your time.